Let's wait for a couple of minutes. After that, I will start the session. So we may start now. So welcome to the NPTEL live session. This is our fourth session. So welcome. Let's wait for a couple of minutes. After that, we will start. Can you please let me know if I am audible or not? Please let me know if I am audible or not. You can also write in the chat box also. Okay, good evening. So this is our fourth NPTEL live session. I welcome you all. And in the last session, we discussed about plate load tests and all. I solved some problems related to plate load tests. So in today's session, I'm going to talk about soil structure interaction. Okay. So I hope you have gone through all the lectures of week 6. If not, you can go through them later on. In today's session, I'm going to solve some problems. You will get a brief idea, and you are advised to go through all those lectures so that you can understand all the derivations. And today, I am going to help you to solve the problems. So if please follow the problems closely because these are a bit complicated problems. And if you follow the problems, the process closely, you will be able to solve the assignments very easily. Okay, so let me introduce myself once again. My name is sinjandebnath. I am a PhD student in the Department of Civil Engineering at IIT Kharagpur. So let's get started. So let's go to the first question. What is the first question? An infinite beam of cross section 0.25 meter by 0.2 meter. This one is breadth, this one is height, subjected to a concentrated load of 100 kilonewton. Calculate the deflection of the beam at the point of application of load. The bending stiffness of the beam is this 1.67 into 10 to the power 3 kilonewton meter square, and K0, that is the subgrade modulus, that is 60,000 kilonewton per meter square per meter. So infinite beam, okay. Actually, in soil structure interaction, strip footing, that means long strip footing where the length is very long. That type of footing can be represented using infinite beam. Okay. Strip footing can be represented mathematically using an infinite beam. So what is an infinite beam? I will just brief a bit, and you are recommended to go through all the lectures, because in the lectures, if you follow the lectures closely, you will understand all the derivations and all. I am just going to brief a bit about infinite beam. So strip footing, you all know the length of the strip footing is very long compared to its breadth. Okay, so the so this B and H, the 0.25 meter and zero point 0.2 meter, this is the cross section of the beam. This is the cross section. Okay, so uh, okay, so how does the infinite beam look like? So like this, the direction is x. This one is x-axis, along x-axis. This one is plus infinity towards, this one is minus infinity towards minus infinity. And here it is saying that are subjected to a concentrated load of 100 kilonewton. So you see the beam, the length of the beam tends towards infinity in this direction also and this direction also. So we can say, we can assume that 100 kilonewton is acting at the middle. 100 kilonewton is acting at the middle. Okay, so this one is P, let it be P. Okay, and the point of application, this, the reference point, we will name it x equal to 0. See, this is along x-axis. Towards this side it's positive infinite, and towards this side it is negative infinite. Okay, so at x equal to 0, 100 kilonewton is acting. So we need to find the deflection of this beam at the point of application. That means at this point, we need to find the deflection. Okay. The bending stiffness of the beam is given, that is the EI value, and K0 is also given. Okay. So let me write all those down over here. So load that is acting P, the load that is acting P, what is the value of P? It is 100 kilonewton. The cross section of the beam, this one is B. What is B? B is 0.25 meter. This one is B, 0.25 meter. This one is H. H is zero point 0.2 meter. Since a strip footing can be represented using an infinite beam, that's why we need to solve such problems on infinite beam in order to get some confidence while solving those problems, okay, related to strip footing in this way. So this is the H, this one is the B. And what are the other things? The bending stiffness of the beam, that is EI. What is EI? EI of the beam is 1.67 into 10 to the power 3. 1.67 into 10 to the power 3 kilonewton meter square. Okay. And what is K0? That is the subgrade modulus. It is 60,000. K0 is 60,000 kilonewton per meter square per meter. Okay. So first of all, let me just talk about infinite beam. So suppose this is the infinite beam. Positive infinity, and load is acting over here, that is P. Okay, so actually the general equation of the beam, okay, for deflection, the general equation of beam for deflection, the deflection can be represented by W. The derivation of this you will get in the lectures. So W is equal to e to the power lambda x. I will explain everything. First let me write it down. E to the power lambda x C1 cos lambda x plus C2 sin lambda x plus e to the power minus lambda x bracket open c3 cos lambda x plus c4 sin lambda x. Okay, this is the equation. Suppose this is number 1, and this lambda is equal to 4 root 4 k by 4 ei. This k, what is k? K is equal to width of the beam into the subgrade modulus of the spring. Actually, this is c. Actually, c. What is k0? K0 is the subgrade modulus. Okay, subgrade modulus of the soil underneath. And remember one thing: the footing can be represented by using infinite beam, and the soil can be represented using spring. Okay, so K0 is a subgrade modulus. It can also be said that it is the spring constant of the spring that is representing the soil. Okay, so K0 is that actually. So B into K0 is equal to K. This is the equation. Now this is the general equation. This is not the equation for the infinite beam. We need to derive the equation for the infinite beam for deflection. Okay, this is the general equation of deflection for a beam, not infinite beam. So for infinite beam, we need to find out all the constant, that is C1, C2, C3, C4 using boundary conditions. We need to apply the necessary boundary conditions. If we apply the necessary boundary conditions, we will get the equation for deflection for the infinite beam. So what are the boundary conditions? One minute. So what are the boundary conditions? C, in this diagram C, look at this diagram. This side is tending towards negative infinity. This side also tends towards positive infinity. Okay, so this one is infinite beam. So for infinite beam, as x tends to infinity, deflection also tends to 0. Okay, this is the boundary condition. Okay, if this beam is very long, at, at a position which is very low, very far away from this point, suppose from point P, at that, if we apply load over here at a very far away point, suppose at a very far away point in this side and in this direction also, at those points the deflection will be 0. It's obvious. So that is why as x tends to infinity, the deflection also tends to 0. Okay, fine. If we apply these two boundary conditions in this equation 1, we will get C1 equal to C2 equal to 0. Both the constants will be 0. Okay. So if both the constants are 0, then what will be the equation? W is equal to this part only. So let me write it down. So after applying the necessary boundary conditions, we get C1 equal to C2 equal to 0. That means W will be equal to e to the power minus lambda x C3 cos lambda x plus C4 sin lambda x. Okay, suppose this one is equation 2. Okay, so now there are also two constants C3 and C4. In order to eliminate these two boundary conditions, with these two constants, we need to apply more boundary conditions, right? So what are the other boundary conditions? So one boundary condition is the slope. Okay, the slope at this point where the load is acting. At this point, like I told earlier over here, this is the reference point where x equal to 0. Okay, so here x is equal to 0, and this side tends towards positive infinity, and the other side tends towards negative infinity, the left hand side. So at x equal to 0, the slope is 0. This is a boundary condition. Okay, so dw by dx. Dw means w is the deflection. So change in deflection by the change in this length. So that is the slope. So so the slope at x equal to 0, slope at x equal to 0 is 0. This is a boundary condition. So if we apply this boundary condition, if we, if we differentiate this w and equate this w, differentiate this w and equate it with 0, we will get C3 equal to C4. Okay, the both the constants are equal, we will get. So let me just term it as C. Okay, since both the constants are same, we can write it like this: C3 is equal to C4 is equal to 2. So what will be the equation? Equation will be, if we just apply, insert C3 is equal to C4 is equal to C over here, we will get W is equal to e to the power minus lambda x. Just take the C out of the brackets. So into C into cos lambda x plus sin lambda x, right? Now the C, this constant is still unknown. So for that we need to apply another boundary condition. After that, this C will be eliminated. Okay, or else actually not eliminated, we will get the value of C, which will incorporate into the equation. So what is the another boundary condition? C, in this beam, I am applying the load over here. Okay, I'm applying the load over here. That means the subgrade, the what I just told earlier, what I have just told earlier, there will be soil underneath this beam. Then the soil can be represented using springs. So that means there will be springs like this. And what happens in soil? You are applying the load on the footing, and the soil is also providing resistance, right? So the springs like soil will also provide resistance. So if we just, since this is symmetry actually, since load is acting at the middle, we are just considering the left part or the right part. Okay, like this part or maybe this part. Just consider any one among them. So if we consider half of the model, we will get, we can write it like this, right? 0 to infinity, like from this 0 to infinity. I'm going towards positive side. Okay, from this side to this side. So from 0 to infinity, if we integrate the reaction forces, so what is the reaction force? If k is the subgrade modulus of the spring constant of the spring, okay, of the springs, then the reaction will be k into deflection. Okay, now if we integrate the reaction from this to this, we will get the total reaction acting between these two, from 0 to infinity. Okay, so we are integrating the reaction forces from 0 to infinity. What is the reaction force? That is k, that is subgrade modulus into deflection. Okay, dx. Now the reaction forces will be opposed by the point load. So the whole P is acting over here over the whole length. So that means we can say the reaction forces acting only only on the right portion is counteracted. The reaction forces acting on this part is being counteracted by P by 2.
Excuse me, sir.
Yes, tell.
The slide is not visible at all, and we are not able to follow whatever you are telling to.
Oh, you should have told me earlier, na. I wrote a
I
lot
had
of
sent you
things.
twice, sir. I had sent you twice the message.
Oh,
Okay, sir.
oh, oh, I didn't see. Okay, okay. You should have just asked me earlier. Okay, 1 minute. Okay. Um, so shall I start from the beginning? Okay.
So
So
briefly, you can.
okay, because this needs to be okay. Wait a minute. Wait a minute. Wait a minute. Can you see the slides now? Hello.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So see. First, let us look at the question first. an infinite beam of cross section 0.25 meter by 0.2 meter subjected to a concentrated load of 100 kilonewton. Calculate the deflection of the beam at the point of application of the load. The bending stiffness of the beam EI is equal to 1.67 into 10 to the power 3 kilonewton meter square, and K0 is 60,000 kilonewton per meter square per meter. Okay, so what is happening is that, see, this is the beam, right? This is the beam, and load is acting over here. This is the reference point x equal to 0. You will get all the information in the lectures. I am just briefing. I have not started the problem yet. So the load is acting at the reference point, and the x direction, the right part is tends towards infinity, positive infinity, and the left part also tends towards negative infinity. Okay, this is a very long beam. A strip footing can also be represented using an infinite beam, a very long strip footing. So that's why we are solving these types of problems in order to understand these calculations better. Okay, so see, this is a very long beam. So the in, the informations which are given. So the informations that are given in the question is the load that is acting over here, it is 100 kilonewton, and we know the EI, that is the bending stiffness of the beam, which is 1.67 into 10 to the power 3 kilonewton per meter square. And K0, what is K0? It is the subgrade modulus. Okay, subgrade modulus means since a strip footing can be represented by a beam mathematically, the soil can also be represented using springs. Okay, and K0 can be defined as the spring constant of the springs, and the subgrade modulus, you know what is subgrade modulus of the soil. You get it by using plate load test and all. So that's all actually. So see, this is the beam. So this is the general equation of deflection. This is not the equation for the infinite beam. This is the equation of deflection for this is generalized equation of deflection. Okay, we need to apply the necessary boundary conditions in order to get the deflection for the infinite beam or semi-infinite beam and all. We need to apply the necessary boundary conditions. Okay, so this is the general equation for deflection. That is e to the power lambda x c1 cos lambda x plus c2 sin lambda x plus e to the power minus lambda x c3 cos lambda x plus c4 sin lambda x. Okay, and lambda is equal to root 4 k by 4 ei. What is the value of k? K is equal to b into k0. What is k0? K0 is the subgrade modulus, and this b, what is b? B is the b is the breadth of the beam. Okay, the beam that we are considering. So what are the necessary boundary conditions for the infinite beam? See the right see, look at the left part and the part. Okay, see, if let's look at the right part first. See, as the this is the x is the along the length, the direction along the length of the beam. So we are applying, suppose this is extending towards positive infinity, and this part is this free end. All these two are free ends, because this is an infinite beam, and this part is extending towards negative infinity. Okay, so if we apply a load over here, a point very far away from the application of load, point of application of load, at that point the deflection will be very minimum, or 0 tends to 0 actually, if we apply load over here. So that is the boundary condition, first boundary condition, that is, as x tends to infinity, deflection tends to 0. Okay, if we apply this boundary condition in the equation 1, we will get c1 and c2 equal to 0, both will be 0. Now if we incorporate these two constants, that is the value of these two constants, that is 0, c1 and c2 equal to 0 in equation 1. In this equation, if we put c1 and c2 equal to 0, we will get w equal to e to the power, this part only, e to the power minus lambda x c3 cos lambda x plus c4 sin lambda x, right? This part. Fine. Have you understood till now? Till this part? Please let me know if you guys have understood till this part. Okay, fine. So now let's come to the next boundary condition. See, at the point of application of load at this point, which is x equal to 0. See, this, see, we can say that we can say the reference point is equal to x as x equal to 0. We can say it like that because the right part is extending towards infinity and the left part also. So you can say, since both the parts are are extending towards infinity, we can say that the load is acting at the middle. So we can say that is the reference point, that is x equal to 0, and the right part is tending towards infinity and the left part is also tending towards negative infinity, right? So the reference point x equal to 0 where the load is actually acting. So you can say the another boundary condition is that at the point of application of load, that is at x equal to 0, the slope will be 0. So dw by dx, that is the change in deflection and also the change in the length at that point is equal to 0. Okay, at x equal to 0. So if we apply this boundary condition, like if we, this is the equation, see, look at equation number 2. If we differentiate w with x dw by dx and equate that with dw by dx equal to slope, if we equate that with 0, we will get c3 is equal to c4. Okay, now let us write it down like this: c3 equal to c4 equal to c. We let us term it like this. Now if we just put this c into this equation, equation number 2, okay, that we got after applying the initial boundary conditions, we will get this only: e to the power minus lambda x into c into cos lambda x plus sin lambda x. See, the c is still unknown. That means we need to apply another boundary condition in order to get the value of c. Okay, so have you understood till now? Please let me know so that I will proceed further. Please let me know if you have understood till now.
Hello, sir.
Yes, tell me please.
Please repeat this boundary condition. How this dw by dx is 0 at
See,
x is
see,
equal to.
see. Uh, uh, See, the load is acting over here, right? The load is acting over here. If you plot the deflection curve like this, the if you plot the deflection curve, the tangent over here, the slope of the tangent will be like this, right? If this is a deflection, this is the beam, suppose this will be the deflection. If we draw a tangent, it will be like this. And what will be the slope of this tangent? It will be 0, right? So that means at the point of application the slope is 0. If you follow, if you suppose if you refer to structural engineering, the deflection pattern of simply supported beam is also like this. Have you understood?
Yes, yes, it's clear.
Okay. So now can you say, so now let us just consider, see, x equal to 0. That means P is acting at the middle. So now let us consider a half of the beam. Suppose this half or maybe this half. Suppose let us consider this half only, the right hand part. Okay. So see, load is acting, P is acting, and the soil is also providing resistance in through the springs. Okay, the soil is also providing resistance. So we can say it like that. If we consider the right hand part, so we can say that the reaction forces. So what is the reaction forces? Suppose this is a spring, right? The spring constant is k or k0. So what will be the reaction forces? The reaction forces will be k into deflection, right? If the spring constant is k and the spring deflection is w, the reaction force will be k into w. And if we integrate it from 0 to infinity, 0 to positive infinity, we'll get the total reaction forces that is giving the reaction on this on the right hand part, right? So the, see, for the right hand part, since P is acting at the middle, the reaction forces acting at the right hand part, okay, from where that is coming? That is coming from P by 2, right? The forces, the see P is acting at the middle. So for the left hand part, P by 2 is acting, we are assuming, and for the right hand part, P by 2 is acting. So P by 2 is getting, getting counteracted by the reaction forces Kw in integration. I'm integrating this from 0 to infinity. So this will be P by 2. Have you understood this concept which I am trying to say? Please let me know. Please let me know if you have understood this boundary condition, this condition. This is the reaction force from 0 to infinity. That is the right hand part, and that is being counteracted by P by 2. That is the load coming at, that is the half of the load coming at x equal to 0. Please let me know if you have understood this or not. Have you understood this? Please let me know.
Hello, sir.
Yes, yes, please tell.
So, sir, not it is not clear that much.
It is not clear that much. Okay, have you seen the lecture videos?
Uh, no, sir.
Okay, so uh, please go through the lecture videos of week number 6. You will understand the derivation also. And in this session, yeah, I have given a brief. Have you understood what is happening actually? The brief.
Actually, I joined at 6:15, so I missed that portion.
Okay, don't worry. Okay, don't worry. Actually, what is happening is that you can model a strip footing. Since the strip footing is very long compared to its breadth, since strip footing is very long, you can represent it by using a infinite beam. Okay, infinite beam means it is a very long beam. Mathematically, I am trying to say mathematically in terms of soil structure interaction. So a footing can be represented by using a beam, and the soil underneath the footing, the soil that is supporting the footing can be represented by using springs. Okay, springs. So K is the spring constant of the spring, that is similar to that of the shear, that is similar to that of the subgrade modulus. Okay, so that is
Hmm.
all happening over here. Okay, so I am just trying to represent all those mathematically. I'm just trying to incorporate everything into the equations. So
And W represent what, sir?
W is the deflection of the beam. Okay, just forget about foundations and soil. Just see, look at this.
Okay.
That is a beam, and load is acting at the middle, at the center point. That is the infinite beam. The left hand
Hmm.
part is tends towards positive infinity, no, negative infinity, and the right hand part tends towards a positive infinity. A very long beam, and a load is acting at the middle, and the deflection at the middle, that is the x equal to 0 part, the reference point, that point the deflection is W. So deflection is W. Okay, and the slope at that point is also 0.
Okay.
So I hope you have understood the brief what I'm trying to say.
Yes, sir.
Okay, and I'm also once again I will also explain this part once again what is happening. So Kw, so if K is the spring constant and W is the deflection of the spring, so Kw means the reaction force that the spring is giving. Okay, so now if we integrate the reaction force from 0 to positive infinity, we will get the reaction forces of this part of the right hand part. Now the reaction force acting on the right hand part uh, is counteracting the force that is coming from above, that is P by 2. Okay, so P by 2 is so P by 2. Okay, so that is all I have written over here. Okay,
Understood.
okay, so let me now just, so this is another equation. So Kw dx equal to P by 2. Now, where was I? So W is equal to this and kW dx equal to P by 2. Okay. So now if you solve this, see, you know W. What is W now? W is this equation. If you just put that equation over here in place of W and solve it, integrate it from 0 to infinity and equate that with P by 2, you will get, let me write it down like this, 0 to infinity k into what is W? W is e to the power minus lambda x c into c cos lambda x plus sin lambda x. See, if we just equate this with P by 2 and solve the equation, you will get k into c P by 2. Wait a minute, please. Okay, so if you solve this equation, you will get the value of c, which we are trying to determine. Okay, so we will get the value of c. So the constant that we are trying to get, so the constant, we will get the constant. So constant will be P lambda by 2k. We know what is lambda. Lambda is this root 4 k by 4 ei. So this will be the value of the constant. This is the value of constant that we are trying to find out, c. Okay, so now just let me put that into equation number, this equation. If we put the value of this constant, if we put this, okay, the value of c in this equation, see, c is unknown. If we just put the value of c into this equation, we will get the equation for w. So what will be the equation for w? The w will be this. Just we are putting p lambda by 2k over here, okay, at the place of c. So p lambda by 2k into this part. So that means w will be equal to p lambda by 2k e to the power minus lambda x e to the power minus lambda x into this part, that is cos lambda x plus sin lambda x, right? So we can write it like this: w is equal to p lambda by 2k into ax, where this part is a lambda x, actually lambda x, since this is a function of both lambda and x, this part is a lambda x, so we can write it like this: p lambda by 2k into a lambda x. This is the equation for deflection for a infinite beam. Okay, so this is it. So what is the question? Let me just go to the question once. So that is all for the derivation. Small brief. Now we'll solve the problem. So a infinite beam of cross section 0.25 meter breadth and 0.25 meter height. This is the breadth, this is the height. Subjected to a concentrated load of 100 kilonewton. Calculate the deflection of the beam at the point of application of the load. So you need to find out W at x is equal to 0. The bending stiffness of the beam is given 1.67 10 to the power 3 kilonewton per kilonewton meter square, and K0 is also given 60,000 kilonewton meter square per meter. Okay, so now we know the equation for deflection. This is the equation for deflection. of a semi-infinite beam. So we'll use this equation to find out the deflection. So how we will use? So first of all, we need to find out Ax, A lambda x, okay? So A lambda x, A lambda x. So look at this part. A lambda x is equal to e to the power minus lambda x and cos lambda x and all plus sin lambda x. Now we need to find out the deflection at reference point. That means at x equal to 0, where the load is acting. So at x is equal to 0, if we put x is equal to 0, this part will be 1, right? This A lambda x will be equal to 1. Fine. So that means the deflection at x is equal to 0 will be p lambda by 2k. We know p, we need to find out lambda and k. Okay. So p lambda, so deflection at x is equal to 0 will be equal to p lambda by 2k. So that is all. So lambda is equal to 4 root over of k by 4 ei. Okay. So 4 root over of k by 4 ei. So what is k? As I told earlier, k is equal to b into k0, where b is the breadth of the beam and k0 is the subgrade modulus, and ei is the bending stiffness. Ei is the bending stiffness. See this part. So we know the value of ei. What is ei? Ei is 1.67 to the power 3. So let me just write it down. Lambda is equal to 4 to the power k. K means b, k means b into k0. That means what is the value of b? The value of b is this 0.25 meters. So 0.25 into what is k0? K0 is K0 is 60,000, right? 60,000. So what will be the unit? K0 is kilonewton per meter square per meter, and B is meter. That means this will be kilonewton per meter square. So this will be equal to 15,000 kilonewton per meter square. Okay. So now let me just put into this equation. So lambda is equal to root 4 15,000. So will be 15,000 divided by 4 into EI. So EI is also given over here 1.67 10 to the power 3. 1.67 into 10 to the power 3. So if we calculate this, we will get lambda will be equal to 1.224. And the unit of lambda is per meter. That means meter to the power minus 1. Okay. So now what we have? See, we have the value of lambda, we have the value of p. We have also the value of k. Now we just need to put all those into this equation. Okay, p lambda by 2k. So W is equal to p lambda by 2k. So what is p? P is 100 kilonewton. P lambda, what is lambda? 1.244224 by 2k. 2, and what is the value of k? The value of k is this 15,000. So if we solve this, we will get W at x equal to 0. It will be 4.08 millimeter. This is the answer. So this is the value of deflection at x equal to 0. That means at the load application point. So please let me know if you have any doubt in this question, or else I will proceed to the next part, next question. Okay. Similar type of question, but here we need to determine the bending moment of the beam. Bending moment of the beam at the point of application of load. In the last question, we are asked to find out the deflection at the point of application of load. In this question, we need to find out the bending moment of the beam at the point of application of load. Okay. The dimensions are same to that of previous question. The breadth is 0.25 meter and height is also same, 0.2 meter, and the load that is acting is also same, 100 kilonewton. Okay, so the bending stiffness EI is also same, 1.67 into 10 to the power 3 kilonewton meter square, and K0, that is the subgrade modulus, is 60,000 kilonewton meter square per meter. So for this problem, we need to use the equation for bending moment. So in the last question, I derived the deflection part. You will get all the derivations in the lectures. Okay, you need to follow all the lectures where you will get all the equations, all the derivations, everything. And you should also know, if you miss the sessions, the live sessions, you will get all the recordings in the NPTEL site. All the recordings are available over there, will be available, and this particular session will also be made available after this session, and all the previous sessions are also uploaded in on the site. Okay, so if you need to follow any session, you can just refer to the site. So let me just use the bending moment equation to find out the bending moment. So for the infinite beam, the equation for bending moment is this. Let me write it down. M is equal to the generalized equation 4 lambda C lambda x, and C lambda x is equal to e to the power minus lambda x cos of lambda x minus sine of lambda x. This is the generalized equation. So we need to find out the bending moment at the point of application of load. So that means at x equal to 0. Okay. So that means M at x equal to 0 at this point. So if we just put x equal to 0 over here, okay, so that means x equal to 0 means e to the power 0. So that means C lambda x will be equal to 1, right? So that means this one will be equal to P by 4 lambda. Okay, so we know the value of P. We know the value of P. What is the value of P? P is 100 kilonewton. 100 kilonewton. And what is lambda? Lambda is equal to root 4. Lambda is equal to root 4 K by EI. What is K? K is B into K0 by EI. So since this is the present question is similar to that of the last question, this is the breadth is similar to that of the last question, K0, the subgrade modulus is also similar, EI is also similar, that means the value of lambda will also be similar. So that means lambda is equal to 1.224 per meter. Okay, it is similar to that of the last question. Okay, where was the value of lambda? See, this part. Lambda is 1.224 per meter. So lambda is 1.224 per meter. So we need to just put all the values over here. So 4 into 1.224. Okay, 100 by 4 into 1.224. So if we just calculate this, we will get M is equal to 20.425 kilonewton per meter. In the last question, we have used the equation for deflection, and in the present question, we have used the equation for the moment, bending moment. So if you have any problem regarding this present question, please let me know. Else I will proceed to the next question.
Hello, sir.
Yes, please tell.
This equation of M is only for this infinite beam, na? If it is a semi-infinite
Yes,
beam, then
yes, yes. For semi-infinite beam, it is different. I will show you. Okay. For
okay.
semi-infinite beam, the equations are different because the boundary conditions will be different, right? See, the generalized equation is same actually. Okay, the generalized equation is same. You just need to alter that by using the different boundary conditions. Okay.
Okay.
Okay. So now let us go to the third question. So what is the third question? This is also an infinite beam, and the geometry is also same. Subjected to a concentrated load of 100 kilonewton. Calculate the deflection of the beam at the distance of 1.5 towards the left side from the point of application of load. Okay, so that means if this is the infinite beam and the load is acting at the reference point x equal to 0, we need to find out the deflection at this point, which is 1.5 meter. Okay, towards the left side. This is the left side, so that means over here. Okay, we need to find out the deflection. The bending stiffness is same, and the subgrade modulus is also same. Okay, so this one is the x-axis. This direction tends to minus infinity. This direction tends to positive infinity. So this is the problem. We need to find out the deflection at this point. Fine. So let me write down the equation for deflection for infinite beam. For infinite beam, the equation for deflection is p lambda by 2k into a lambda x, where a lambda x is equal to e to the power minus lambda x cos lambda x plus sin lambda x, right? So what is happening over here? We need to find out the deflection at this point, which is 1.5 meter towards the left side of the point of application of load. So that means the here what is x actually here in this equation? The x is the point where we are intending to we're intending to find out the deflection. In the last two questions, we were trying to find out the bending moment and the deflection at the point of application of load. So in the last two questions, the value of x was 0. Okay, because we are trying to find out the deflection and bending moment at the load application point itself. In this question, we are trying to find out the point of deflection, which is 1.5 meter towards the left side of the point of application of load. Okay, so that means here the x will be 1.5. Here x is equal to 1.5. So if we use this, first let me find out lambda. So actually you know the value of lambda. The lambda is 4 root over of k by ei. Since the value of ei and k everything is same to that of the previous question, so lambda will be equal to 1.224 meter to the meter per meter. Okay, this is the value of lambda. So we know the value of lambda, and the x, okay, x is equal to 1.5. Okay, so lambda x, what is lambda x? Lambda x is equal to 1.224 into 1.5. This one is equal to 1.836 if I am not wrong. Please calculate this with me. Okay, if I am wrong, please let me know. Okay, so 1.224 into x. X is 1.5. So the 1.224 into x will be equal to 1.836. Okay. So what will be the value of a lambda x? A lambda x is equal to e to the power minus lambda x. So e to the power minus 1.836. Okay. Now inside, see, cos lambda x plus sin lambda x. So cos lambda x. So that means this lambda x for cos and sin terms, we need to convert this into degrees. Okay. So degrees. So that means for the cosine and sine terms, we need to convert lambda x into degrees. That means lambda x into 180 degrees by pi. Okay. So that means 1.836 into 180 degree by pi. If you solve this equation, if you solve this, you will get this. This will be equal to 105.2 degrees. Okay, so we will use this for the sine and cosine terms. So now e to the power minus 1.836 into cos of 105.2 degrees plus sine of 105.2 degrees. Okay, so if you solve this, you will get the value of a lambda x. Okay, and the other part, that is p lambda, this part, p lambda by 2k. You know the value of lambda. This is the value of lambda. Okay, this is the value of lambda. You know what is p. P is, see, let me write it down over here. W is equal to p lambda by 2k into a lambda x. A lambda x, we will get it from here. And p, what is p? P is 100 kilonewton, that is acting over here. P is 100 kilonewton. And lambda is 1.224 by 2 into k. What is k? K is equal to subgrade modulus into breadth, and that is equal to this. Breadth is same to that of the previous question, and also the subgrade modulus, that is 60,000, so that is 15,000. So this one is 15,000. If you solve this, you will get the deflection at x equal to 1.5 from the load application point. The deflection will be 0.46 millimeter. Okay, so that means we are applying load over here, and the deflection, we are applying load over here, and the deflection at this point will be 0.46 millimeter. So you can see the deflection at this point is very small compared to the deflection at x equal to 0, which we solved in the first question. Okay, so this is the answer, the deflection at 1.5 meter from the loading point. Okay, so if you have any problem in this question, please let me know. If you have any doubt, please let me know.
Understood, sir.
Okay, okay. So now let us proceed to the next question, question number 4. So here the geometry is same to that of the previous question. Infinite beam of cross section 0.25 meter by 0.2 meter, subjected to a concentrated load of 100 kilonewton. Calculate the shear force. So here in this question, we need to find out the shear force of the beam. Okay, at a distance of 1.5 meter towards the left side from the point of application of load. The bending stiffness is given over here, and the subgrade modulus is also given. Okay, so what is the equation for the shear force? So shear force can be represented by using Q. Okay, so Q. So Q is equal to P by 2 d lambda x, where d lambda x is equal to e to the power minus lambda x cos of lambda x. Okay, this. So you know the value of p, you know the value of lambda. So what is the value of lambda? Lambda is 1.224 per meter inverse. And here we have been asked to find out the shear force at a distance of 1.5 meter towards the left side. That means x is equal to 1.5 meter. So lambda x will be equal to 1.836 like that of the previous question. And if we convert this into degrees, which will be lambda x into 180 by pi, we will get it 105.2 degrees. So if we just put all this into this equation particularly, so q is equal to actually p by 2 into d lambda x. So what is d lambda x? D lambda x is equal to, what is d lambda x? So what is d lambda x is d, this part, e to the power minus lambda x cos lambda x. So p by 2 to the power minus lambda x cos of lambda x. Okay, so this is the equation. We need to find out the shear force at x equal to 1.5. So q at x equal to 1.5 is equal to p. What is p? P is 100 kilonewton. 100 by 2 into e to the power minus lambda. What is lambda? It's 1.224 into x. So lambda x is this 1.836. 1.836. This is in radians, and 1.836. And now, sorry, not radians. So 1 minus lambda x is 1.836, just integer, and this part. Cosine terms in terms of degrees. So what is lambda x in terms of degrees? This 105.2 degrees. Cos 105.2 degrees. So 105.2 degrees. Okay. If you solve this equation, you will get the value, shear force value, minus 2.1 kilonewton. This is the direction of shear force. So minus 2.1 kilonewton. Okay. So if you have any problem in this, if you have any doubt in this current problem, please let me know.
Hello, sir.
Yes, please tell.
When x is on the left hand side of the point of application of the load,
Yes.
you think that we should take it negative?
No, actually, I am considering, you can take it as negative, but I am considering the left part to be positive. Okay.
Okay.
You will understood this in the derivation clearly. The values will be same, only the direction will be different. Okay, that is not a big thing.
Not a
Okay.
big thing.
Yes, you will the values, you will get the values, only the direction will be different. For the equations also, if you go through the lectures, you will understand. Okay, so
Means if
now,
it is given on the right hand side, then we should take negative as per your derivation.
yes, you can take the negative value. Okay.
Okay.
Okay. Only please follow the lectures for the sign conventions. Okay, the sign conventions are very well explained in the lectures. And so now let us proceed to the next question. This. So here see, instead of load, here a moment is given. So what is the question? An infinite beam of cross section 0.25 meter by 0.2 meter. The geometry is same, subjected to a concentrated moment of 100 kilonewton meter clockwise. Calculate the shear force of the beam at a distance of 1.5 meter towards the left side from the point of application of the moment. The bending stiffness xc, x less than 0. See, x is equal to 0 means at the midpoint, x less than 0 means towards the left. Okay, so left. So the bending stiffness is the same and the subgrade modulus is also same to that of the last question. Okay, x less than 0, that means it is towards the left side. X is equal to 0 means at the load application point or the moment application point, and x less than 0 means to the left side. X greater, if x is greater than 0, that means it is towards the right side. Only the sign conventions will be different, but the equations will be same. Only the values that we will get after solving the equations will be negative or positive based upon the direction. So you are advised to go through the lectures to understand the sign conventions very clearly. So now let us look at this problem number 5. So here a moment is acting, okay? A moment of 100 kilonewton meter is acting, and we need to find out the shear force that is, the shear force that is occurring due to the moment at a distance of 1.5 meter towards the left side from the point of application of moment. The bending stiffness and the subgrade modulus is given. So what is the equation? So Q is equal to minus m0. Minus is for the direction of the shear force, lambda into a lambda x. This is the equation for the shear force due to moment. So this. So what is a lambda x? A lambda x is lambda. This one is lambda. A lambda x is e to the power minus lambda x cos of lambda x plus sine of lambda x. Okay. So this. Now here x is equal to 1.5 meter. Okay. So x is equal to 1.5 meter. Fine. Lambda, it is same to that of the previous question, I believe. The k is similar. The k is equal to b into 0. K is equal to b into k0. The k0 is similar to that of the last question, and the breadth, that is the breadth of the beam, is also similar. That means k is around 15,000. Is 15,000 kilonewton per meter square. Okay, so, and EI, what is EI? EI is 60,000 kilonewton per meter square per meter. So the value of lambda will be 1.224, same to that of the last questions. 4 meter inverse. Okay, so we know the value of m0. What is m0? M0 is 100 kilonewton meter, the moment that is acting. We know the value of lambda, we know the value of x. So now let me just put all the values in the equation. So Q, the shear force at x equal to 1.5 meter towards the left side, will be equal to minus m0. So minus 100 by 2, m0 is 100. So minus 100 by 2 into lambda. So what is lambda? Lambda is 1.224 into e to the power minus lambda x. So e to the power lambda x. So what is lambda x? What was the lambda x in the last question? It is same. Lambda x is 1.836. So e to the power minus lambda x. So e to the power minus 1.836. So cos of lambda x and sine of lambda x. So lambda x in degrees. So cos of lambda x means this one is in radians and this will be in degrees. 1.836 is in radians and 1.836 in degrees is 105.2 degrees plus sine of 105.2 degrees. Okay, lambda is cos of lambda x plus sine of lambda. So if you just solve this, you will get shear force will be equal to minus 6.86 kilonewton. Minus is just the deduction of the shear force. So this is the answer. If you have any problem in this question, please let me know.
Understood, sir.
Okay, okay. Now let us solve the sixth question. See, here it is a semi-infinite beam. Okay. So a soil supports a semi-infinite beam. So in case of semi-infinite beam, we know the boundary condition, so not boundary condition, the fixity condition. In case of infinite beam, the both the ends are free. Actually, we don't know. Actually, we don't know what are the fixity conditions of the infinite beam. Okay, the two ends are free and all the two ends are all the two ends tend towards infinity. Okay, but here it is not the case. Here a end is here one end tends towards infinity and another one is not another one is may could be fixed or free. Okay, so semi-infinite beam with free end. So semi-infinite, this one is a semi-infinite beam with free end. So we know the fixity of a end. Okay, so now in this question we know the fixity of one end, so that end is free and another one we don't know, that tends towards infinity. So as soil supports the semi-infinite beam with free end, the beam carries a point load of 100 kilonewton at a distance of 1.5 meter from the free end. Okay, so calculate the value of deflection in the beam below the point load if the bending stiffness of the beam is 1.67 10 to the power 3. So what is happening is that here there is a semi-infinite beam with a free end. Okay, one end is free and another end tends towards infinity. So the beam carries a point load at 100 kilonewton at a distance of 1.5 meter from that free end. Okay, so let me draw it first. So we know the fixity condition of one end. So this end is free. This one is free end and this one tends to infinity. Okay, positive infinity. X. Fine. So in this question, what is happening is that 100 kilonewton load is acting at a distance of 1.5 meter from the free end. Okay, so that means a load is acting over here. P equal to 100 kilonewton. A load is acting over here at a distance of 1.5 meter from the free end. So x is equal to 1.5 meter. Fine. It is acting over here at a point O. Okay. So see what will happen over here. A load is acting. So a load is acting for due to which shear force and a bending moment will create. Okay, it will create. So in order to counteract those shear force and bending moment, we can assume a load is acting over here. Okay, only for counteracting the shear force and bending moment at the free end, because there will be no bend, because the bending moment and shear force at the free end will be equal to 0. This is a boundary condition. Okay, the boundary condition is that at the free end there will be no bending moment and there will be no shear force. So what will happen? In order to counteract the bending moment and shear force that will generate due to 100 kilonewton, we need to apply some counteracting moment and forces in order to neutralize the shear force and bending moment at the free end. Okay, so here let me just define a counteracting force to counteracting shear force. So P0. Okay, a counteracting force which is given in order to counteract the shear force that is generating at this point at the free end due to 100 kilonewton at point A. Suppose this is the point A. So at point A, we can say another moment we are applying. This is a counteracting moment in order to counteract the moment that is generating due to P. Okay, because there will be no bending moment and deflection. No, sorry, not deflection. There will be no bending moment and shear force at the free end. Okay, this is the boundary condition. So in order to avoid them, we are actually giving the counteracting moment and force. Fine. So this is at a distance of 1.5 meter, x equal to 1.5 meter. So P is acting at a distance of 1.5 meter from the free end. Okay, so P is 100 kilonewton, x is equal to 1.5 meter from the free end. The bending stiffness EI is equal to 1.67 into 10 to the power 3 kilonewton meter square. The subgrade modulus value is 15,000 kilonewton per meter square. Okay. K, this is K, not K0. Okay, so K is directly given over here 15,000. Okay, so now let me just find out the value of lambda because we need it. So lambda is equal to root 4 K by EI. So 4K means 15,000 by 4 into EI means this. So if we just solve this, we will get K will be equal to 1.224 meter inverse. Okay. So this is the value of lambda. So now what will happen? Here we are given counteracting moment, and another moment will generate due to this P which we are trying to counteract. Okay. And also we must okay, so we need to find out MA. This is the moment that is generating due to P. Okay, so what is the moment that is generating due to P? So that is MA. So what is this is MA, this is due to P actually. Okay, due to P means this load. For this load, what is the moment that is generating? It is P by 4 lambda C lambda A. Okay, for a semi-infinite beam. Okay, so in the last question, so we have solved the coefficients was A lambda x, B lambda x. Here is C lambda A. Okay, okay, and here A is 1.5 meter. This the same thing. X is equal to A is equal to 1.5 meter. So P by 4 lambda into C lambda A. So 100. So what is C lambda? C lambda A is equal to similar thing. X is equal to actually A. Okay, X is similar thing, just this one. For semi-infinite beam, X is equal to A. Just the term is different. So C lambda A is equal to e to the power minus lambda A cos of lambda A minus sine of lambda A. Okay, so for x is equal to A is equal to 1.5, 100 by 4 into lambda means 1.224. C lambda, that means this, e to the power minus lambda is same thing, 1.836, similar to that of the last question. Cos of 105.2 degrees, lambda x in degrees, minus sine of 105.2 degrees. If you solve this, you will get the moment due to the point load P. Okay, the moment due to point load P, it will be equal to minus 4 kilonewton meter. This is the moment that is acting due to P. Okay, so what is the shear force? So now we know the moment that is acting due to P. Now we must know the shear force that is acting. Okay, this is the moment. So we must find out the shear force QA. QA due to P. Due to P, load P. So what is the value of QA? QA is equal to P by 2 d lambda A. Okay. So what is d lambda A? D lambda A means e to the power minus lambda A, e to the power minus lambda A cos of lambda A. So that means it will be P by 2 means 100 by 2, d lambda A means e to the power minus lambda 1.836, 836 cos of lambda A in terms of degrees is 105.2 degrees. 5.2 degrees. Now if you solve this, you will get QA will be equal to minus 2.1 kilonewton. The shear force due to P, only P. Now we need to find out P0 and M0. So what are P0 and M0? P0 and M0 are the counteracting, that is the end conditioning. Actually we are trying to counteracting the shear force and moment. So we need to find out those counteracting moment and shear force. So the counteracting moment and shear force will be, there are two equations which we need to use. So P0 will be equal to the counteracting force, that is this P0 and M0. So P0 will be equal to 4 lambda into MA plus QA. Okay. So what is lambda? Lambda is 1.224, 1.224, and what is MA? MA we just found out it is 4, right? 4. So 1.224 into 4, actually it's minus 4, so just minus, so minus. So minus 4 plus QA. What is QA? QA is minus 2.1. So minus 2.1. Okay. So now, so if you solve this, you will get P0 is equal to minus 28 kilonewton, the end conditioning force. Okay. So now we need to also find out the M0, that is the end conditioning moment, this M0. So what is the equation for M0? So the equation for M0 is equal to minus 2 by lambda 2 lambda MA plus QA. Okay, you can find out, you can you can see all the derivations in the lectures. You will get everything, the how the end moment, how this end conditioning moments are working, and how these are coming, the derivations you will all get. So the lambda we know. So now let us just put all the parameters, the values of all the parameters into the equation. So lambda is 1.224, 1.224. So 2 into lambda means 1.224 into MA. So what is MA? Ma is the moment due to P, that is minus 4 kilonewton. So minus 4 plus QA. What is QA? QA is this, minus 2.1 kilonewton. Minus 2.1 kilonewton. Okay. So if you solve this, you will get the value of M0, that is the end conditioning moment. It will be equal to the equation, the end conditioning moment will be equal to 19.43 kilonewton meter. Okay, 19.43 kilonewton meter. So this one, the P0 is minus 28 and M0 is 19.43. These two are known as end conditioning force and moment. Fine. So now, after finding out the end conditioning force and the moment, we need to, so what was the actual question? We have found out all this thing. We need to find out the deflection, the value of deflection in the beam below the point load. That means below the point load, if the bending stiffness of the beam is this. So actually what we need to do is that we need to find out the deflection below the point load. Okay, so below the point load over here. So for that we need to do all this. You will understand. So now this one is A, this direction, this particular distance is A or X, which is equal to 1.5 meter. So at 1.5 meter from the free end, so the beam carries a point load of 100 kN at a distance of 1.5 meter from the free end. So we need to find out the deflection at this point at 1.5 meter from the free end. Okay. So now see W, the deflection at X is equal to A. That means at A, point A, which is 1.5 meter from the free end. So what will be the deflection? There will be three terms. Okay. So for the in the diagram you can see the 100 kN acting, the load P is acting. So for P there will be deflection. For the end conditioning moment there will be deflection at point O. At point O there will be deflection for the load that is acting, that is P. For the moment M0, the end conditioning moment, there will be deflection at point O. For the end conditioning force, that is PO, there will be deflection at point O. Okay, need to we need to add up. We need to add up all the deflections due to P, P0 and M0 in order to get the deflection at point O. Okay, so deflection at X equal to A. So the equations, if we just add up all the deflections, you will get P lambda by 2K. This is the deflection due to load P, that is the 100 kilonewton, plus P0 lambda by 2K into A lambda A. This is the deflection that you are getting due to end conditioning force, that is P0. And next is M0 lambda square by K B lambda A. This is the deflection that you are getting due to end conditioning moment. Okay. So now we need to we know the value of lambda, we know the value of K. We have found out the value of P0, M0. So sorry. So we need to find out the value of A lambda A and B lambda A. Okay. So A lambda A. A lambda A is equal to e to the power minus lambda A cos of lambda A plus sine of lambda A. Okay, so that means e to the power minus lambda A in radians, that is 1.836, cos of lambda A in degrees, that is 105.2 degrees, plus sine of 105.2 degrees. If you solve this, you will get A lambda is equal to 1.112. Okay. So now we know this part. So another part, B lambda A. What is B lambda A? Let me just add a slide over here. So A lambda is equal to 0.112. So what is B lambda A? B lambda A, the equation is e to the power minus lambda A sine of lambda A. Okay. So e to the power minus lambda A in radians is 1.836, and e to the power and sine of lambda A, this lambda is in degrees, that is 105.2 degrees. If you solve this B lambda A, you will get 0.154. B lambda A will be is equal to 0.154. Now we just need to put all the values of all the parameters in this particular equation. Okay, so W at x equal to A. So W at x equal to A will be equal to P lambda by 2k. So P is 100. P lambda by 2k. P means 100. Lambda means lambda is 1.224 by 2k. What is k? K is k. The k is given here in the question. That is the subgrade modulus into breadth. Directly it is given 15,000. So k means 15,000 plus P0. What is P0? That is the end conditioning force. And what is the end conditioning force? We have found out end conditioning force is minus 28 kilonewton. This one. So minus 28 kilonewton. So P0 lambda by 2k into A lambda. P0 lambda. What is lambda? Lambda is 1.224 by 2k. 2 into 15,000 by 2k into A lambda A. What is A lambda A? A lambda A is equal to 0.112. So this one is 0.112. Okay. And the third part, what is the third part? M0 lambda square by k into B lambda A. So M0 is the end conditioning moment. End conditioning moment. What is the end conditioning moment? It is 19.43. So plus 19.43 into lambda square, I believe, lambda square by k. So lambda means 1.224 square. Okay, 1.224 square by k. K means 15,000. Okay, into B lambda A. B lambda A means 0.154 into 0.154. Okay. Now, if you solve this, you will get the deflection at point A. That means deflection at the loading point, which is 1.5 meter away from the free end. At that point, at x equal to A, you will get the deflection 4.25 millimeters. Okay, so this is the answer. So I know this is a very long problem. Several things you need to calculate over here. So if you have any problem, you can tell me now. If you have followed this question properly, please let me know if you have any doubts.
This part is clearly understood, sir.
Oh, you have understood everything in this problem.
Means whatever equations and all you have used, so I just assume that all the equations are derived in the lecture, so
Yes,
that I
yes, yes,
will.
yes. Oh, yes, yes.
We
Oh,
have
okay.
only that is, if instead of free end in
Yes.
the given beam, if some support is acting, that then what are the changes which will be there?
Actually, we are assuming actually in the free end there will be no, actually see, at the free end there will be no shear force, right? There will be no shear force. So, but for P0, that is the load is acting. In order to avoid the shear force, we are giving some moment and we are giving some counteracting force in order to counteract the moment and shear force that is coming from the original load that is acting. Okay, that is the P, that is 100 kilonewton. So we are just uh, giving some counteracting moments, we are assuming, and after that we are mathematically calculating those in order to finding out the deflection. Actually the derivation is like that. We need to assume like this P0 and N0, and we need to find out those P0 and N0 in order to find out the original deflection at the load application point, and also the slope and moment, all those things. Okay.
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 But instead of free end, something means some kind of support is there.
Yes,
It
yes.
is given.
Then the equations will change. Then everything
Yes,
will
sir.
change. Okay.
Okay, that I wanted to know.
Yes, yes. Then everything will change. Okay. So these are all the problems, and after that there are two short questions which I have posted over here. So the next question. So this question, what is the question over here? Question number 7. This is a short question. Strip footing of width B and length L. In case of strip footing, the length is much greater than that of B, is analyzed as a beam under plane strain condition. Okay, so that means we are just analyzing strip footing in plane strain condition. Okay, so what is plane strain condition? I will tell. What would be the length and width of the beam? Okay, we are assuming a strip footing to be a beam. Okay, we are just trying to solve a strip footing problem using soil interaction process. So what is a strip footing? A strip footing is a very long footing. We know the breadth B and the length is very long compared to its breadth. Okay, the length is very long compared to its breadth. Okay, so if you recall the last lectures, the last bearing capacity lectures, while we were calculating the bearing capacity of the strip footing, we were using per meter length. So can you please recall, when we are finding out the bearing capacity of the strip footing, we are using the length to be 1 meter or per 1 meter. We were finding out the bearing capacity like kilonewton per meter. Okay, for unit length in case of strip footing. So can you recall? Please let me know if you can recall that concept.
No, sir. Yes.
If you go through the last lectures or last sessions, last 2 or 3 sessions, you will understand that for strip footing, the length is very long. Okay, so length is very long. So all the bearing capacity, all the things, or the bearing capacity that we are finding out, we were just finding out for the unit length. That means for per meter length of the strip footing. Okay, we are considering the length to be 1 meter for per meter length. For per meter length, we are finding out the bearing capacity. Okay, since the length is very long, we are finding out the bearing capacity of the strip footing for 1 meter length. Okay, this is the rule actually. So here that is actually the plane strain condition. See over here. See the length of the strip footing is very long, and so in order to analyze this type of problems, we can assume that this B, okay, the B, since B is much smaller, we can assume that this B is the length of the footing. The B is the length of the footing like this, and this L is out of the plane. Okay, out of the plane means like this towards your screen. L is out of the plane, is acting out of the plane towards yourself, actually towards you. So That means we can say the length is 1 millimeter, unit length. Yeah, in order to analyze these problems, we assume length to be 1 meter, to be unity. So in these types of problems, the width of the beam, we consider width of the beam to be the length of the beam, and the length we consider to be 1 meter. If you go through the last sessions, you will see while calculating the bearing capacity of the strip footings, we have used this concept. We determine the bearing capacity of the strip footing in terms of kilonewton per meter, not kilonewton. For isolated footings, for square footing, all those things, with the bearing capacity, the unit of the bearing capacity was kilonewton only. But for the strip footing, it was in terms of per meter length of the footing. Okay, please go through the last lectures, you will see. So this is it, and you can go through the books. It is also written in the books, this breadth and length case of the strip footing. Since the length is very long, we consider it to be unity. We find out the bearing capacity in terms of unit length of the footing. Okay, so have you understood what I am trying to say?
Yes. Means that means the answer will be L and B will be 1 meter. Or you
Yes,
can
no. Actually, see, if we try to solve the bearing capacity equation, we need to, if we try to solve the bearing capacity equation, if we actually for load, suppose you are asked to find out the allowable load. Sorry, this is the allowable load for the footing. Okay, so suppose you consider a square footing or isolated footing or a rectangular footing having length and breadth B and L. So for a rectangular footing or isolated footing or square footing, what is the allowable load? What is the unit of allowable load? It is kilonewton, right? But for a strip footing, the allowable load you get in terms of kilonewton meter. I am showing you how. What is the bearing capacity of equation? It is C and C and the shape factor depth factor plus Q into NQ plus zero point 0.5 gamma B and gamma, right? This what is the unit of this is the bearing capacity, right? So the allowable load, okay, for a rectangular footing, the what is the allowable load that you get, or the allowable load, or the load that the ultimate load, let's say ultimate load. So what is the this is the ultimate bearing capacity factor, the ultimate bearing capacity equation. So what is the ultimate load that you get if this is a rectangular footing? It's Q into B by L, right? Am I right? Q into B by L. This is the ultimate load that is acting on the footing. If Q is the ultimate bearing capacity, it's Q into BL, right? If this is a rectangular footing. Hello?
yes, sir.
Yes. If QU is the ultimate bearing capacity of a rectangular footing, if we multiply QU with B into L, you will get the ultimate load. Okay, the ultimate
Yes.
load
Yes.
that the rectangular footing can handle. So what will be the unit? The unit is kilonewton,
Yeah.
right? Right?
Yes.
But for strip footing, we used to do this. You see, we did it, we in the question the length was not given. The length of the strips, it was mentioned in the
Assume that
question.
it is 1 meter.
Only the breadth of the footing was mentioned in all the questions.
Yes.
Only
Hmm.
it was mentioned that the a strip footing of breadth something, thus only this. So for those questions, we used to do like this: QU into BL by L. That means per meter length. So QU into B. That means kilonewton per meter square into meter. So kilonewton per meter. Because that is a plane strain problem.
Yes, sir.
Okay, so actually we were considering its breadth only, not length. Length was unity. Okay, so that is why. That is, if you just go through the last sessions, you will just see. Okay, just go through the last one to the last session number 2 and 3. You will just go through the problems. You can see this. So this one is the last question, a very simple one. the lowest plate size that should be used for the plate load test. I hope you know what is the lowest plate load test, the size of the plate that is used.
I think 30 centimeters or
Yes, yes,
30.
yes, 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 30 centimeter. This is a very
Yes.
short question which I just gave. It is 30 centimeter only. So the only the below 30 centimeter plate shouldn't be used. Okay, below 30 centimeter and greater than 70 centimeter. Okay, so that is all for today. So if you have any question regarding the today's session, you can just tell me now, or you can just post in the discussion forum. You can also mail me, and all the videos are available in the YouTube. All the sessions are available in YouTube, and also the links are given in the NPTEL site. You can just log in and see all the sessions over there. So that is all for today. See you in the next sessions next week. Okay, so goodbye for today.
Okay.
Okay,
Thank you so much for solving our small queries, sir.
okay. If you have any query, you can tell me now. Okay, tell me if you have any
Right
query.
now, there is no query about it
Okay,
because I
so
need to go through all the lectures and also.
okay. So your advice to you, please go through all the lectures and post your doubts in the discussion forum, or else you can just drop me a mail. My mail ID is given in the lectures over there. I can also give you my mail ID over here. See, I'm writing actually. My mail ID is sinjan debnath debnath sinjandebnath @gmail.com. Another one is same ID @iitkgp.ac.in. Please drop me a mail if you have any doubt. Okay, in these two
Okay, sir.
IDs. Okay,
Okay.
okay,
Thank you, sir.
okay. Thank you. Goodbye.
Goodbye.